So today our topic is going to be soils. Some of you are majoring in agronomy, some of you are minoring in agronomy, crop sciences, and you may be taking a course in basic soils agronomy 2040 or 20 or CSES 2040 or CSES 2043, and so you'll learn a lot more than what I'm going to give you here today. But soils, we're going to give you a brief overview of soils and some of the more important attributes of soils and why they are certainly it's hard to you cannot overstate the importance of soils in agriculture because that's where all the plants grow. Now, before I do this, I would like to just briefly review some stuff I was talking about yesterday or at the previous lecture. And the issue that we were talking about was photoperiodism. This is what we mean when plants are responsive or flower in response to photoperiod. And I know I gave you a lot of very confusing stuff about short day and long day plants, but right now all I want to do is sort of summarize a little bit of that and to tell you what you really need to remember. And basically there's a couple of things here we need to know, and those is some plants flower in response to shortening days, and these are short day plants, and some flower in response to lengthening days, and these are long day plants. And the thing that you need to remember is that short day plants tend to be warm season. In other words, plants that are planted in the spring and harvested in the fall. That's what a warm season crop is. It grows during the summer months. And examples, of course, are corn, soybean, and cotton. Long day plants, on the other hand, tend to be cool season. And they are basically seeded in the fall and harvested in the spring. And basically their main growing time is the fall winter. Let's say not fall winter, because they're generally dormant during the winter, but the fall and spring. They generally grow vegetatively during in the fall months, and then reproductively during the spring. And the thing is, and warm season crops are no different. They'll start out growing vegetatively, and then they will progress to reproductive growth or flowering as the time tells them to do so. So it is this response to day length that tells plants when to make this transition, or how to make this transition from vegetative to reproductive growth. And so with short day plants, remember that the longest day of the year is June 21. This is the longest day. And with long day plants, the shortest day of the year is December 21, the shortest day. And so, generally speaking, what we try to do for these warm season short day plants is plant them somewhere prior to June 21st. They'll grow vegetatively. And then at some point after June 21st, the days begin to get shorter. So for example, for soybean in Alabama, the thing is that regardless of whether you're talking about short day or long day plants, there is a critical photoperiod. A critical photoperiod. All of them. Now, just because you have a short day plant does not mean you have a critical photoperiod that is less than 12 hours. It just means that you have a critical photoperiod that anything shorter than that makes the plant flower. This critical photoperiod for short day plants. So you may have a critical photoperiod up here of 14.5 hours. And so any day length, any exposure to light that is shorter than that is going to cause this plant to flower. If you have a long day plant with a critical photoperiod of say 12 hours, I'm just making these numbers up because whatever the critical photoperiod is going to depend largely upon the latitude of adaptability. Because remember that at various latitudes, day lengths vary greatly. So it's the latitude of adaptation that generally will determine what the photoperiod, the critical photoperiod is. But if you have a photoperiod, say, of 12 hours, you have a long day plant, and you have a critical photoperiod of 12 hours, that means that any photoperiod longer than 12 hours is going to make it flower. So that's really all you have to remember, is that with short day plants, given a critical photoperiod, anything that long or shorter, short day, anything that long or shorter makes it flower. With long day plants, anything that long, whatever the critical photoperiod is, or longer, will make it flower. That's the key thing you have to remember. And again, it doesn't, whatever those critical photoperiods are does not have anything to do with whether it's a short day or a long day. It is shorter than that or longer than that, depending upon whether you have a short day or a long day plant. Now, on our last lecture, I know I talked about that it's not really the length of the light period at all, it's the length of the dark period. And it's important to know that, because so many of our plants are photoperiodic, and we can manipulate, with a little knowledge, we can manipulate their especially in artificial environments, we can manipulate their reproductive responses. Poinsettias are a famous example. Everybody's familiar with poinsettias, the green and red plant that we all buy at Christmas. Well, that's not when they want to flower. They would rather flower at some other time of the year. But we grow poinsettias in commercial greenhouses and alter the day length on them to make them flower, to produce those beautiful red petals so that they'll be ready in time for Christmas. You can Google it and find out, and it'll tell you all about that if you want to. Moving along here to soils. I didn't mean to digress, but I thought I should go back and give a little better explanation of this photoperiodic response, because it is very important. We can define soils, that part of the Earth's crust where plants grow. So that's a pretty broad definition. Just about anything where it's got a plant growing in it can be considered a soil. It may not be very good soil. It may not be soil like what's in this photograph here, a nice, dark, earthy looking, very texturally satisfying, very good feel, very good tilth. A lot of terms there that really just don't make a lot of sense to a lot of people, but very dirty looking soil. But that's what it is. And this is some very good soil. But any soil is also defined as a natural material derived from weathered rocks, and that's what happens. You have weathered rocks and organic matter that provides water. That's what it does. It provides water, nutrients, and anchorage for land plants. So, a few things about soil. We need some basic understanding of soils to fully understand how plants function. Oftentimes, when plants are not performing well for some reason, there's a soil-related reason. Now, if you look at soil, and it appears to the uneducated as an inert substance, and a lot of people call it dirt. We had a professor here several years back who really detested that word, and he would not allow it to be used in his classroom because it's not dirt, it's soil. Dirt is something that's in your house or in your clothes or something like that. It's not soil. It's a dynamic, chemically active, constantly changing environment that supports a wide variety of life within itself. Soils are very, not only biologically active, but chemically active as well. There's a lot going on there. That's why in this department we have somebody whose specialty is the microbiology of soils, for example. And we have another professor here whose specialty is the chemistry of soils. And they have very active research programs still. We don't know all there is to know about soil microbiology, nor all that we need to know about soil chemistry. And of course, our standard of living depends on the soil. There are a lot of famous quotes out there that about if you don't preserve your soil, you're going to destroy your civilization, and that's been found to be the case in a lot of cases. A lot of our previous civilizations, going all the way back to the very earliest Babylonian Empire, where they irrigated out of the Tigris and Euphrates rivers, they didn't do it in a correct way. They destroyed their soil, and of course their empires went down after that. But we also know that soil is not an absolute requirement for plant growth. You can grow plants hydroponically, but we can't do that very well yet, at least on an economic scale. Most of our crops, while we can, you can go to Disney World and see their hydroponic garden, and you can eat vegetables and lettuce and things like tomatoes that have been grown hydroponically. We just can't economically now grow corn, soybeans, and wheat hydroponically and do it in an economic way. We still have to use the soil. So some of the things that happen that you might find in a typical soil with regard to biological activity, there's going to be lots of microbes in there. These would include your bacteria and other things, and of course the fungi are also considered to be microbes. They are a type of microbe. There's a lot of fungi. There's a lot of microbes. There's a lot of even burrowing animals, for example, are down here. They're doing things to the soil. They're making holes. They're making macropores in the soil. Earthworms. A healthy soil will have all of this. An unhealthy soil will have less of it. You've got a lot of insects that are there that are living in the soil. Plant roots that live in the soil. There's an interesting exercise that they use, and we probably should at some point demonstrate that in this class. But you can take a sample of soil, say a cup of soil, and remove it from where it is out of the ground, and there's a certain chemical that you can add to that is very let's say annoying to everything that lives in that soil. And as a result, when you add this chemical, I think it's something to do with mustard, you add this chemical and all these things that are in this soil will come to the top, and it's just amazing to see. And it's also interesting to know that the amount of biodiversity again is indicative of the health of the soil. One of the things that we can do in agriculture, and one of the things that we have done in agriculture a lot, is to destroy the health of the soil with our agricultural practices. And we're learning still that the best thing to do to soil is pretty much to leave it alone. A lot of tillage is not good for soil, for example. And the more you till the soil, the more you lose your organic matter. And if you want a good, healthy soil, if you want to know if a soil has good health, dig up a sample of it and look and count the number of earthworms. And if you don't see a lot of earthworms in there, that's not a very healthy soil. And you can add fertilizer and you can add water and you can grow plants, but the more biodiversity you have in that soil, the better. And so soils are very biologically dynamic. What do soils do? They function as a medium in which plants grow and are anchored, of course. They store nutrients and water. And one of the things that we will observe as we go through this lecture is that soils differ greatly in their ability to store nutrients and water. Some soils can store a lot of nutrients and hold a lot of water. Some soils cannot. I give you the example of beach sand, for example. If you've ever been on the beach and you wet beach sand, the water will just go right through it. It does not hold that water one bit, and so you can dry it out very quickly. So that's an extreme type of poor water holding capacity soil. But most soil, rest of the soils that we see inland, have varying capacities to catch and hold water without allowing it to pass through. Components of soil. Soils are composed of four major parts. We have our mineral matter, which composes about 45% of the soil. This is going to be the stuff that the soil was originally derived from, the non-organic fraction of the soil. And then we'll have about 25% of that soil that's going to be occupied by either air or water, depending upon the water status of the soil. When the soil is moist, it'll have more water. When the soil dries out, it'll have more air and less water. There's a lot of pores in amongst all these soil particles that are spaces where air and water hangs out. And then we have this organic matter, and we would say that this would be approximately 5%. It can vary from 0 up to greater than 5%, as much as 10 to 12% in some cases. But 5% organic matter is a pretty high number. It would be a very high number for most Alabama soils. If you go up to other areas of the Corn Belt where they have longer winters and soils are derived from different materials, they may have organic matter contents of over 5%. So the relative proportion of organic matter and mineral matter vary greatly. And again, the relative proportions of air and water vary greatly depending upon soil wetness. So let's look at mineral matter first. It's again derived from the inorganic sources, weathered rock, weathered minerals, or whatever the parent material happens to be. And one of the things that's going to be determined here at this point when all this stuff is broken down is what the soil particle size is. And particle size is one of the things that we look at when we're evaluating a soil. It has a great deal of influence on many soil properties. And mainly we derive our particle sizes and we divide particle sizes into sand, silt, and clay. And here's a sand, for example. And these pictures are kind of hard to determine what these particle sizes are. I'll look at that in a minute. But loam soil is generally a mixture of sand, silt, and clay, some different varying proportions. And then a clay particle. This scale here is totally incorrect. Just disregard that entirely. But a clay particle is generally a very small, microscopic, a very small particle of soil. So let's look at what these particle sizes are. Fine sand and sands are anything that's 0.05 millimeters in diameter and up. Anything between 0.002 and 0.5 millimeters is classified as a silt particle. Anything less than 0.002 millimeters is defined as a clay particle. So down here's a representative relative soil particle size, and we do include things that are bigger, but we don't usually find these in agricultural soils. Gravel, for example, is something that is about 2 inches, pieces that are about 2 inches in diameter. Sand particles, these are millimeters, by the way, not inches, sorry, 2 millimeters or bigger in diameter. Sand is, as I said, about 0.05. Silt is going to be a silt particle compared to a sand particle is going to be very small, and a clay particle is going to be invisible at the scale that we're using here. And generally speaking, the important thing here, the important attribute of these different particle sizes, sand, silt, and clay, those are the ones you have to remember, is that the chemical reactivity of these particles is inversely proportional to their size. In other words, this one has the least chemical activity, and clay has the most chemical activity. By chemical activity, we mean how much they react and participate in chemical reactions, primarily how much they react to mineral nutrients and how the ability that they have to catch and hold those mineral nutrients. And we'll deal with that subject here in just a minute. So it is the relative proportions of sand, silt, and clay. You got three things here that are making up this soil. They can occur in various percentages. In other words, you can have 33% of each. You can have 50% clay, 25% silt, 25% sand. You can have 60% sand, 20% silt, and 20% clay. These relative proportions is what is going to be the determining factor for soil texture, which is a major attribute of soils. And one of the things that you have to, if you're looking at a soil, one of the first things you want to do is try to determine what your soil texture is, because that has a major impact on the productivity and the uses for that soil. Now, if we look at this information is going to be found on page 44 of your text, and on the next slide, here's our soil textural triangle. This is copied out of your textbook, for example. And these are your textural classes here. You have everything from a sand to a loamy sand to a sandy loam, sandy clay loam, a loam, silt loam, clay loam, silty clay loam, a silty clay, a clay, and a sandy clay. These are your soil textures. These are all different soil textures. Anything with the word loam means that it's a mixture, relatively balanced mixture of all three. Usually the best soils are classified as loams. A loam soil is generally one of the best soils that you can have because it's sort of heavy on the sand. Now, as far as what proportions of each of these is in each one of these soil textural classifications, you look at this bottom one here and you'll see percent sand, and you follow the line here so that anything that is 40% clay passes right through loam, and you see another line here. If you go up here, you see that it's 40% silt. So if it's 40% clay and 40% silt, that's going to make it a loam. And by subtraction, it must be 60% clay. Well, that makes no sense whatsoever. Um, actually, I followed the wrong line. This is the line you need to follow here. It's 20% clay. Yes, that's why I have these helpful arrows over here. This is the way you go with the clays. This is the way you go with the silts, and this is the way you go with the sands. These graphs and things that you see in the textbook, this one, for example, does not have these very helpful arrows. That's why they're in there. These are your sand lines, these are your clay lines, and these are your silt lines, and these are your clay lines. So if you know the proportions of any two, you can, by subtraction, get the proportion of the third. They always have to add up to 100, and you can find, for example, the particular texture of the soil. How do we determine these percentages? Well, they have experimental methods that are fairly simple and straightforward, given a soil sample to determine what the percentage of sand, silt, and clay is. Clay has a major impact here. You'll notice that anything that's above 50% clay, for example, is classified as a clay almost always. There's a couple of exceptions here, but anything that's more than 50% clay is a clay. Anything that's more than 30% clay generally will have the name clay in it, and some of them will have the name clay in the texture, even if it's less than 30% clay. Sand has very little influence on the name. To be a sand, it has to be at least 85% sand, and the other two components are very, very small. And to be a silt, it has to be, silt is a little more influential, but not quite. There are some silt loams, mostly what we have in Alabama, first of all. If we want to look at most of what we have in Alabama, we have mostly sandy loams and mostly loamy sands, especially in South Alabama. We have others. We have some sandy clay loams. We have some clays out in the Black Belt. Other areas you go to in the country, you're looking more at silts up in certain areas of the Midwest. They also have a lot of clay loams and silty clay loams and some of these other textural classes. The other thing you have to be considered, not only with soil texture, and we're still talking about mineral matter here, not only is soil texture important, but soil structure. And this is how the individual soil particles are arranged into stable aggregates. You can take a soil and you can compress it and pack it and squeeze all the air out of it and all the water out of it, and you got a soil, basically, this is an extreme example, but you've got a soil there that has very poor structure. This is one of the things that we do when we till soil, is we drive tractors and we drive heavy machinery over it all the time, and we compact and we alter the soil structure and we change the soil structure. You want as much air and water space in there as possible. And one of the ways you get that is by, one of the things that affect soil structure are going to be plant roots growing through that soil. Some of the soil organisms, the fungi with their mycelium, earthworms, how much organic matter you have, weather, freezing and thawing of soils tends to, the water expanding and contracting with freezing and thawing will have an impact on soil structure. And again, as I said, you can destroy soil structure by poor management practices, heavy machinery, soil compaction, erosion. When you remove the topsoil, the soil that has the best structure is the topsoil. We haven't really talked much about soil profiles, but basically, if you look at a cross section of any soil, you're going to have the top layer here is the topsoil. Actually, you have up here, you're going to have some crop debris, plant debris. Then you have your topsoil. And then you have below that, you're going to have various layers of subsoil. These are parts of the soil that have not been tilled. Plant roots can certainly grow down into this area, but most of your organic matter is up here in the topsoil. And if you remove that, you get a soil down here that has much poorer qualities with regard to a lot of the things that we need soil for. Down here is your, what they call the sea horizon. These are various horizons, by the way, and this may be just derived from the parent material. So soil pore size is going to be determined by both texture and structure. Remember, texture is particle size, or the relative proportions of the three particle sizes. Structure is determined by the again, it's sort of a hard thing to define, but it's the amount of pore space that is there as a function of how much that soil's been how much that soil is biologically active and how much has been compressed and compacted. Pore size affects how much water soil can hold, which is the water holding capacity of the soil. Water holding capacity is a very important soil attribute. Water holding capacity, because in most of our systems, most of the agricultural systems that we have nowadays are dry land systems. We don't have a lot of irrigated land. We have some, but most of our agriculture depends on rainfall. And the more water you can hold in a soil, the less often it has to rain. And not only that, not only does it affect water holding capacity, how much water that a soil can hold, but it affects the infiltration rate, how rapidly that soil can absorb water. If you have a soil that has a poor infiltration rate and you have a thunderstorm, most of that water may run off, and that's not going to do you any good. Not only does it run off, not getting into the soil profile, but it carries with it nutrients, and it carries with it topsoil, and it carries with it pesticides and any other thing that you may be trying to use to help that crop grow. And it also impacts the ease with which roots can penetrate the soil. So we're looking at a couple of things here. Water holding capacity. The more water holding capacity and the higher infiltration rate, the better the soil is able to hold, to absorb water during a rain event, and hold that water. And that's what you need to have with a good soil. You want it to absorb the water as it comes down. You want it to hold on to that water. And that's the ability of a soil to do that is going to be primarily determined by the soil texture and the soil structure. Let me back up just a minute because I'd like to say something else here when we talk about texture. Generally, those soils with sandy texture, again, referring back to my example with beach sand, they do not have very good water holding capacity. Now, they may have a good infiltration rate, but you don't necessarily have to have. What you want is both good infiltration rate and good water holding capacity. And these things are not only going to be impacted again by soil texture and structure, but also by the organic fraction of the soil. This is the fraction, the organic matter is the fraction of the soil that is derived from living organisms. Dead plant roots, dead bacteria, living mycelial fungus, dead fungi. And again, the organic fraction, organic matter fraction can vary considerably from one soil to the other depending upon how that soil has been treated and what environment it's in. And generally speaking, when you have higher rainfall and areas of higher precipitation, you have more organic matter versus areas of low rainfall, simply because you have more biological activity in a high rainfall area. Where you have higher temperatures, you're going to have less organic matter because you have a lot of biological activity operating at a very high level, breaking down this organic matter. Again, we do get the high rainfall here in Alabama, but we suffer the higher temperatures, and so we have an environment that causes most of our soils to be around 2% organic matter. Many of them that have been farmed for many years are 1% or less. Some of the poor soils, for example, are 1% or less organic matter. And of course, the other thing that causes variations in organic matter is the tillage, how much you till the soil. Lower organic matter is caused by tillage because you are incorporating that crop debris. Really, is what this should be, not necessarily. Crop debris is the stuff that's left over after you harvest a crop, and some people classify that as organic matter, and some people do not. Some people put it into a separate classification because it needs to decay some before it can become organic matter. But once you till that crop debris under, invert the soil, put the crop debris under, and have a smooth, weed-free crop debris free surface, you incorporate that organic matter and it causes faster decay down beneath, and that again can harm the overall organic matter content of that soil. This is something that we do. Now you might say, those of you who are not as familiar with crop production systems, you would say, well, don't we till all of our soil? Not necessarily. We'll talk about that when we look at tillage in a few days. So some of the different types of organic matter, here we talk about how some of these things are classified. You have your litter, crop debris, or crop residue. You know, there's lots of different terms: crop debris, litter, crop residue. Here it is. This is what we're talking about here. This stuff here, this is dead plant material. This brown stuff here is dead plant material, but it's protecting that soil surface. It's preventing weeds from coming up. It's providing competitions to weed seedlings that may germinate. It has a lot of good benefits. And then right below that level is going to be your duff. And the duff and the humus are both substances that really classify as organic matter. Duff is in a stage of decay. Humus is organic matter that is resistant to further decay. And compost is an example of something that could be considered to be a humus. If you've composted material to where it's not decaying anymore and you add that to soil, you can really improve the physical properties of that soil by the addition of this organic matter. So these are the three things, and generally, again, litter is not generally recognized as organic matter. It will become organic matter at some point once it begins to decay. But all three of these, you want as much of all three of these as you can possibly get to improve the productivity of the soil. It will do a lot of good things for you. What does it do? What does organic matter do? One of the things it does, it is an important source of plant nutrients. And these organic materials, as they break down, will release things like nitrogen and phosphorus. You recall that DNA has both of these elements in it. So anything that's breaking down, any organism that has DNA in it is going to be a source of nitrogen and phosphorus. So it is an important source of plant nutrients. It improves soil structure. Organic matter, again, this is sort of like soil structure is sort of related to soil tilth, and it's kind of it's related. This particular example given here is relating it to moisture content. When you in your soil in your hand will form a ball and stay there, or you can't form it into a ball at all, or it can be you can form it into a loose sort of structure there that you can break with your thumb. But either way, what organic matter does for you, and this is the important thing, it improves soil structure. It improves the infiltration rate. Very important, remember. It improves the soil tilth, the ability for it to be tilled. And last but not least, and probably the most important, it improves the water holding capacity of the soil. Soil of higher organic matter will hold water better than soil of lower organic matter. People are finding this out as they modify their tillage regimes nowadays in Alabama and till the soil less. They find that their organic matter improves. Their plants are more resistant and are better able to withstand periods of drought than they would be able to otherwise. The importance of organic matter cannot be overemphasized, and the importance of organic matter in a soil productivity, from a soil productivity standpoint, cannot be overemphasized. It just does so many good things for you. That's why gardeners, for example, are big into compost. And if you're a gardener and you're not composting your kitchen waste, then you're doing yourself a disservice. The best soils, I'm telling you from experience, the best soils are soils that are high in organic matter, that are well composted. And you can create artificial environments pretty quickly in your garden by adding organic matter. It's a little more difficult on a large-scale farming operation, but it can be done through tillage modification. And don't be under the assumption that I don't need to compost these things. I can just add plant debris to my soil and it will improve its productivity. That is not the case. In other words, you can't go out into the woods and collect a bunch of leaves and just incorporate that into your soil and expect it to improve your soil's productivity. The soil has to be in, the organic matter has to be in some stage of decay. It has to be composted. This can cause a lot of problems. People get into a lot of problems by putting some of these types of things into their soils, because what happens is that these things start to break down, but they tie up all the nitrogen so the plant can't get it, and you may have some real issues that way. So let's talk about soil water. All the water that's used by plants is going to come from the soil, and there are different types of soil water as it exists in the soil. We have gravitational water. Gravitational water is really water that is on the way through. That is, it's water that is going to is added to the soil, and it is not held by the soil. It's free water. That's why it's called free water. It is not held by the soil. It moves through the soil with the force of gravity, and so it stays in the soil only temporarily. A soil immediately after a rainfall event has a lot of gravitational water in it. Now, once that gravitational water passes through the soil with the force of gravity, what you have left is available water, two types of water, available water and unavailable water. Available water is also called capillary water, and is held in these soil pores by capillary forces. It's available to plants, and they're going to get this water. This is what they're going to, actually, gravitational water is available too, but it's not going to be there long enough to do the plant much good, because it's going to pass through the soil relatively quickly, within a few hours or so, depending upon the depth of a rain event. There's also unavailable water, also called hygroscopic water. These are water particles that are held so tightly to soil surface that they're held by chemical bonds and they're not available to plants. If you take a soil and you put it out on your kitchen counter and you allow it to dry, it is not completely dry. It may look dry to you, it may feel dry to you, but it's still got water in it. The only way to drive off that water, that hygroscopic water, is to put the water in an oven and literally bake it off, and that's the only way to get rid of it. But plants, unfortunately, cannot use this unavailable water. At saturation, and we can describe soils with regard to their water status by several different terms here. One of those terms is a soil being at saturation capacity. One of them is a soil being at field capacity, and the other is a soil being at the wilting point. Again, these are referred to and discussed in Table 5-1, page 52 in the text, and they will show you the water content for various soil textures. In other words, the water content of a sandy loam at these various states versus the water content of a clay loam at these various states. At saturation capacity, all the pores are filled. This is again going to be, soil is saturated with water. It's immediately after a rain or irrigation event. Much of the water here is gravitational water. It's going to pass through. When you remove all the gravitational water, the soil is said to be at field capacity. So what I'm talking about here is we've got different types of water, and then we're talking about soil water status based on these different types of water. As the soil dries further, due to the plants uptaking the water, surface evaporation from the soil surface, eventually the plant gets to the point where it can no longer extract the water. You get to the point where the only water in the soil is hygroscopic or unavailable water, and that soil is said to be at the wilting point. The plant will start to wilt at this point. So your goal should be, as a producer, is to keep your soil somewhere between field capacity and the wilting point. Plants will be just fine if you do that. So here's a little bit about another diagram here. As you have your gravitational water and you're at saturation, as the water drains through, you got your water held in these micropores here. Your available water there. You have capillary water. This soil is at saturation, moving toward the wilting point where the remaining soil adheres to soil particles. Here's a graph from your textbook. As you move from a sand to a clay, the percent water, different types of water, either your unavailable water or your available water, changes dramatically. What happens is and this is amount of water that's here, or the percentage of water. Either way, you see that as you move from a sand to a sandy loam to soils with various higher percentages of clay, you have more available water. You have more water altogether. So you can see here the influence of soil texture on water availability and the amount of water that's available. See sands over here, these sandy loams, which we have, a lot of sandy loams, especially in the southern half of Alabama and on up in parts of the northern Alabama too. We just don't have the water holding capacity that they do, for example, up in the Midwest, where they have silt loams and so many silt loams and clay loams up there in the Corn Belt. Even though they get less precipitation than we do, their soils hold water, so much more water, and so much more available water than ours do. Saturation again, all pores are full, gravitational water is draining out, and you can do this, you can demonstrate this. Lots of different demonstrations out there. Field capacity available for growth, and the wilting point, no more water is available. Soil air, believe it or not, soil does have air. Believe it or not, roots need air to breathe. Roots actually respire. They don't photosynthesize. All they do is respire. So they have to take in oxygen, and they will give off carbon dioxide during that process of respiration. Because of that, you generally have a little higher CO2 content in soil air than you do in atmospheric air, because you don't get quite the exchange between the atmosphere and soil air. You've got your microorganisms down there also respiring. All of these are the roots, and the microorganisms are all creating CO2 in the process. You may have oxygen issues in soils with poor structure. As your soils become compacted, they don't contain as much air. You'll get poor drainage, poor infiltration of oxygen into those soils. And we're going to wind all this up by talking about some of the chemical properties of soil, a couple of things that we need to know here, because this is going to be related to nutrients and nutrient management in soils. You have soil pH, which is the concentration of hydrogen ions in the soil, the acidity of the soil. pH range on a normal pH scale ranges from 0 to 14. pH of 0 is the most extreme acid condition. The pH of 14 is the most extreme alkaline condition. The pH is the negative logarithm in the base 10 of the molar hydrogen ion concentration. For example, a pH of 4 here, as indicated, pH of 4, your hydrogen ion concentration is going to be at 0.0001 molar. That's 1, 2, 3, 4 decimal places away from a 1 molar hydrogen ion concentration. That would be a pH of 0. pH of 5 has 1/10 the hydrogen ion concentration of a pH of 4, and a pH of 7 has 1/100th the hydrogen ion concentration of a pH of 5. So every time you get a pH unit change, as you move upward in the scale, you decrease your hydrogen ion concentration by a factor of 10. So each change in pH, single number, either up or down, is a tenfold increase or decrease depending upon whether that pH goes up or down. Commonly, pHs range around 4 to 10, although you can get soils with pHs of lower or higher than that. Most crops, as we saw when we were talking about nutrients in the nutrient lab, prefer pH to be in the range of 6.0 to 7.3, just slightly on the acid side. And of course, there are different crop species will differ in their optimum pH requirements. Legumes are especially sensitive to low pH soils because of their nitrogen fixing bacteria don't like those types of soils. Watermelon, azaleas, blueberries, and other crops prefer low pH. They like acid soils. Again, nutrient availability is affected by pH. We saw that in lab. Some nutrients become unavailable or may become more soluble, more available to the point of becoming toxic at too high or too low a pH. Here's a pH scale down here showing the pH of various things: battery acid, stomach acid, lemon juice or vinegar, And here we go into the normal, what we call the normal range, and you've got things like acid rain, pure water is at 7, seawater has a pH of 8, baking soda has a pH of 9, and some of your drain cleaners and bleaches and things like that have very, very high pHs. How do we adjust the pH in soil? How do we change it? How do we make it better? When soil becomes too acidic, in other words, and this is the common problem, your pH is too low, generally goes below 6, it may become necessary to add lime, agricultural lime. This is agricultural lime here, calcium carbonate. This is a naturally occurring mineral, can be mined. It's even mined here in Alabama. You can put that on your soil. It will decrease the pH or increase the pH, raise the pH according to the following reaction. This carbonate ion here, when the lime gets into the soil, it will dissociate into its various ions. It will dissociate into calcium plus CO3 minus. That should have a different, I can't recall whether this is supposed to have 2 minuses on it or not. I have to check on that, but I believe it should have 2 minuses. What you have is you have your carbonate ion combining with water to give, again, you'll get a hydroxide ion here and a bicarbonate ion here. Yes, that should have two minuses here. This H plus, this extra hydrogen, remember if we're trying to raise the pH, we have too much of this, will combine with your bicarbonate to give you hydrogen or carbonic acid here. This will dissociate and then break down into carbon dioxide and water. Your OH fraction here will combine with hydrogen ion concentration, hydrogen ion, to give you water. So basically what this does is it reduces these hydrogen ions into what you'll eventually get is CO2 and water as products. The other thing that we have to be concerned about from a chemical standpoint of soils or chemical reactivities of soils is the cation exchange capacity, or CEC, most often abbreviated as CEC. It's the measure of the chemical reactivity of the soil. It's the ability of clay, mostly the clay particles, mostly the organic fraction, to react and hold positively charged ions or cations. Remember, an ion is a charged molecule. And all of these minerals, these nutrients that we see, are going to exist in the ionic form in the soil. Calcium, magnesium, potassium, hydrogen, aluminum. Aluminum's not a nutrient, but it's still there. There are others. These all have positive charges, as you'll see. And so they need in the soil, to be able, for the soil to be effective in holding these things, you need clay and organic particles that carry negative charges. And that's what clay particles do. They generally have clay particles, generally have negative charges, as do clay particles. So they attract and hold these cations. And these cations can be replaced and exchanged. When you take one off, you have to replace it with another. For example, potassium. When a potassium ion is held in place by a clay particle, in order for the plant to get that potassium ion, it's going to have to give it something in return, and most often it will donate back to that clay particle a hydrogen ion concentration, a hydrogen ion. Different types of clays and thus different soils will differ greatly in their cation exchange capacity. And this thing about low pH, when you have low pH, remember you have a high H plus concentration. H plus, being a cation, will occupy sites on the soil particles. And if that site is occupied by a hydrogen cation, that means it cannot be occupied by a potassium, a magnesium, or a calcium ion. So when you have a low pH, you reduce the number of potential sites that can be occupied by nutrient cations. So here's a clay particle. Most clay particles can be represented as disc. They're very small, remember, But the surface of that clay particle is surrounded by these negative charges. There are negative charges all over here. It's just the nature of the clay particle. And they're going to be attracted to ammonium ions. This is a source of nitrogen. Again, hydrogen ions, calcium ions, hydrogen, magnesium. Don't show any, in this particular diagram here, don't show any potassium, but certainly potassium is an important ion that can be occupied here by one of these cation exchange sites. So the factors that affect CEC. Soils differ greatly in their CECs, their cation exchange capacities. One of them is soil type. The type of soil that you have. Different types and amounts of clay, different amounts of organic matter. For example, a sandy loam, a Norfolk sandy loam, this is a soil series name, occurs in Alabama, has a CEC of 3. Now I won't tell you what the units are. They're milliequivalents per mole or something like that. I don't recall exactly, but 3. Loam, a loam soil, has got a little more clay content. Here's your sandy soil, sandy loam soil over here with 10% clay, 10% silt, and a bunch of sand in it. Your loam soil has got a little more clay, a little more silt, and a little more sand. It's going to have a CEC. This is a New Jersey soil of 14. A clay loam from either Cecil, Alabama, can be either 5, or it can be a Susquehanna soil, can have a CEC of 34, much, much greater. So just the fact that it has more clay does not necessarily mean it has a higher CEC. It depends on what kind of clay it is. A Houston soil in Alabama, that's over in West Alabama, and the Black Belt, its CEC is 50. A well-rotted compost, and this shows you the value and the contribution of organic matter to the CEC. Remember I said organic matter improves water infiltration rates, it improves the soil structure, it improves water holding capacity, it improves cation exchange capacity. So soils that are low, have a low CEC, like a sandy loam, like a Norfolk sandy loam in South Alabama, are inherently have lower fertility and productivity. And in fact, if you go back in history, one of the things that made a lot of these soils more productive in South Alabama and southeast Georgia in the coastal plain, they weren't very good for farming until people developed commercial fertilizers. And when they developed commercial fertilizers, then these soils could be fertilized and would grow things pretty well, particularly if they were supplied with enough water. Again, here's your nutrient availability chart as related to as a function of soil pH, ranging from 4 to 9 in this case. As your pH generally, for these important nutrients, as your pH goes down, nutrient availability becomes less. For these micronutrients, as your pH goes up, nutrient availability becomes less. So you need, again, to be operating somewhere in this range, preferably in your soil. Here's an Alabama soil map. Alabama is a very diverse state with regard to soil types. We have the coastal plain here. This is the coastal plain, and you have your lower coastal plain here divided by, cut in two by the Black Belt area. This is your upper coastal plain here. Upper coastal plain soils will stretch all the way up to the very northwest corner of Alabama. The Black Belt soils are very clay type soil. They have a very high clay content. This is generally considered to be the Black Belt area of Alabama here, but it also stretches and it goes over into Mississippi as well, almost all the way across the Alabama, and you can find patches of Black Belt here over in the eastern sections. You have your Piedmont, basically the foothills of the Appalachians here, your limestone valleys and uplands here, and your Appalachian plateau soils here. And then the little blue areas here are your alluvial floodplains, alluvial areas. These follow the rivers in Alabama. These are areas that have traditionally flooded, and you'll get deposition during these flood events, and so these soils are generally highly productive. And you'll find these areas as you go up through this eastern section of Alabama and into places like Marion County, for example, where they have a lot of these floodplains. You would never usually not consider these areas as being highly agriculturally productive, but there are some areas up there that do have very good soil. These floodplains are generally very good soils. So Alabama is very diverse in the types of soils that it has. That's all for this lecture on soils. I realize it's been kind of long. Maybe you took a break in the middle. I could have used one. But we're going to be talking about some of these concepts as we move forward. When we talk about water, we've still got to talk about water. We've still got to talk about nutrients and their availability. And so we're going to rely on a lot of the information that we have presented here in this lecture today.